So we talked about entropy yesterday and the fact that it was and how it was related to disorder, for lack of a better term. But you should be aware that you are going to be asked to calculate this stuff. So this formula here, you do not have to memorize. It will be given to you in the back of the AP, or all on the periodic table for my test, and it will be given to you in the AP exam booklet. But the value for entropy is expressed as joules. Is expressed as joules per mole per Kelvin. Okay, so that's how it's expressed, and that tells us a little bit about what we're going to be doing with it and how it works. So we're going to move forward to the next slide, which talks about example number 2. And example number 2 says that we're going to use the formula that we just talked about to calculate the entropy change in the following reaction. So in this case here, I've given you the standard entropies of a couple of the reactants and the products. And remember, this notation right there tells you that it's standard. And when it's standard, what does that mean? 1 atmosphere, 298 K, 1 molar if it's a solution, right? So in this case here, we're going to calculate the change in entropy, which is the sum of the entropy value for, in this case, the products. So N2O, well, I got that carried away. So N2O plus NO2 minus the sum of the entropy change of the reactants, but in this case, it's 3 times the NO because of the coefficient. So when I go to plug this in, the N2O is 219.7 joules per mole Kelvin, plus the NO2, which is 239.9 joules per mole Kelvin, minus the sum of 3 times the 210.65 joules per mole Kelvin. So when I go ahead and do some fun math here, I get an entropy change of negative 172.35 joules per mole Kelvin. Now, that negative value tells me what about the reaction? It's becoming more organized? Yeah. Well, we're going to talk about the won't happen more coming up in a second. Moving forward. So your chemistry life in the future, that is, when you go to college, there's a chance that you're going to have a professor who will refer to things as being spontaneously favored or non-spontaneously favored. And I'm going to talk about how that's important to know now versus later. But you should understand that if a reaction is spontaneous, it will occur by itself. And spontaneity is not necessarily related to rates. So if the reaction occurs by itself, it doesn't necessarily mean it's going to happen fast. It just means it's going to happen.
So like if something's rusting, would that be spontaneous?
Something rusting would be a spontaneous reaction, yes. Now, a non-spontaneous reaction is something that needs continuous input of energy in order for this to occur. And what that means is that we have to add energy for this reaction to occur. So if a reaction is thermodynamically favored, that is spontaneous in one direction, it is not thermodynamically favored in the other direction. So looking at the reaction below, sodium plus chlorine makes sodium chloride. That is thermodynamically favored the way that it's written. However, the reverse of that is not thermodynamically favored. That means that we have to add energy in an effort to make this happen. Okay? Any questions about that? Now, another statement is one of the things that would be really, really awesome is if this was true, okay? Exothermic reactions are usually thermodynamically favored, but there are many endothermic reactions that are also thermodynamically favored. So change in enthalpy is not necessarily the best predictor of whether or not a reaction is going to occur or not. Okay? So spontaneous is the term that is actually used in your textbook. It's also used in most textbooks. It'll probably, like I said, it will also be used by your collegiate professor. However, the College Board wants you to use the term thermodynamically favored instead on the test. So if you write spontaneous and don't use the phrase thermodynamically favored and you are 1000% correct, they will not give you credit for it. Okay, now, a thermodynamically favored does not necessarily need to happen fast, but it can, as long as it occurs on its own at specified conditions without adding any additional energy. The reaction below is thermodynamically favored, but it occurs so slowly that it doesn't appear to happen at all. So what I'm telling you is that over time, diamond will eventually change to graphite. That's a thing that's going to happen. So one could reason that the graphite in your pencil was once diamond. However, it's just going to take so long that in your lifetime and my lifetime, you will probably not notice that it's happened or not. But it is thermodynamically favored in that particular case. So we are going to continue moving forward. Kinetic control is a term that we use when a thermodynamically favored reaction doesn't necessarily occur quickly. So the reaction above doesn't necessarily occur because the activation energy is so high, which makes the overall rate constant incredibly small. Remember rate constants? Small rate constants meant what? That meant what? That reactions did what? A rate constant less than 0 means what?
Oh, this does not bode well for the AP.
That's okay. We'll get there. It means that the reaction is going to either not happen or go very, very slow, right?
Oh, that's what I said.
Now, with that in mind, the issue is that it's when they're under kinetic control, that means that reactions will definitely happen, but they're going to happen over time. Now, the more important portion of this particular lecture is the idea of Gibbs free energy. Gibbs free energy is designated as G, is used to determine whether or not a reaction is thermodynamically favored. The formula for Gibbs free energy calculation is G is equal to enthalpy minus temperature times change in entropy. But Gibbs free energy combines the enthalpy and entropy terms in an effort to give a single measurement of a thermodynamically favorability of a reaction and the energy change associated with it. Yee. So, some things to remember. If delta G's value is less than 0, the reaction is thermodynamically favored to occur spontaneously. Okay? If delta G is 0, the reaction is at equilibrium. That means that it is going forward and backward. If delta G is greater than 0, that means the reaction is not thermodynamically favored, but the reverse reaction is thermodynamically favored. Okay? So those are things you're going to have to remember. Remember the standard free energy change is at standard conditions, and remember standard conditions is the pressure is 1 atmosphere, 1 molar for solutions, and 25 degrees Celsius or 298 K. Now, this formula here will be given to you on the AP exam. Will also be given to you on the test for this unit, so you don't have to worry about that, but you do have to know how to use it. which means we are gonna move forward. Oh, that's not what I wanted. Question?
Are we using a new one for every single one?
No, just whatever you got. Now, here's an example of using Gibbs free energy calculation to determine whether or not a reaction occurred. So at some point or another, you may have noted, or you can look at this particular reaction for sodium becoming sodium and chlorine ions, and you'll see that the delta H is positive, and delta H being positive means it's a what type of reaction? It's endothermic, which means that energy has to be put in to make this reaction occur as we understand it. However, when we did the hand warmer lab, you may have noticed that that the sodium chloride dissolved, even though it had a high delta H, meaning that it shouldn't dissolve because it's endothermic, meaning we have to put energy in, right? However, in this particular case, I'm telling you that the delta S for this particular reaction, its entropy value, is positive 43.17 joules per mole per Kelvin. So when I plug those values in to the Gibbs free energy calculation, I get a value of a negative 8.89 kilojoules per mole. I just randomly picked 295K, just picked it, okay, 'cause it's kind of around room temperature. So the issue is that the negative delta G value tells me that the process is thermodynamically favored, even though it would appear that it probably shouldn't be, simply based on the enthalpy value. Do you follow that? Yes, no? Okay, so we can also predict the temperature at which we can stop dissolving stuff, or the threshold for which stuff will dissolve by using this formula. So in this case, I put delta G equal to 0, because at 0 we said that it's that the system is at what? At equilibrium. So if I'm saying that the system is equilibrium, I am no longer able to dissolve or undissolve stuff. So I went through and I calculated the temperature at which that occurs. The temperature at which that occurs is 89.9 Kelvin. This is the threshold at which it is thermodynamically favored to dissolve salt in terms of temperature. Now 89.9 Kelvin, subtract 273 from that, is ridiculously cold. What state of matter is the ice going to be at that point?
Ice.
Thank you for not making me feel, yes, it's going to be solid. And what I mean, but the important thing that you should remember is that you should be familiar with the fact that if we put salt, certain salts on ice in the wintertime, they tend to do what? Well, what they really do is they increase the freezing point so that they don't melt, and as a result of that, they dissolve into it. So 89.9 is the threshold at which we can no longer dissolve salt into the water system.
I hope it never gets
Ivan.
cold.
So for all delta G equals delta H, delta S, is it if you go, for every one of them, will it be a temperature above what you find will be favorable and anything below will be unfavorable?
Correct.
So at all times?
The question was, if you're solving for temperature here, at that temperature and above will be favorable, below that temperature will be unfavorable. Okay? Yes, JR?
So anything lower than that would make the salt not dissolve?
Correct. All right, now, this chart is also similar to the chart I have over here on the door that I've had up here all day, all school year.
Yeah, I looked at it.
Well, that chart and this chart are very similar, they're not exactly the same. So let's talk about this. If the energy is, if the reaction tends to be exothermic, we would say the sign of the enthalpy is negative. At that point, the entropy condition would be more disordered. If the entropy condition is more disordered, we'd have a sign of delta S being positive. The value that you would get when you calculate delta G will be negative meaning that it is spontaneous at all temperatures. Doesn't matter what temperature it is, the reaction is thermodynamically favored. If it is endothermic, if the reaction is endothermic and the delta H is positive and there is less disorder, that means that the delta S will be negative, then when you do the math on that, your delta G will be positive, and it's not thermodynamically favored at all temperatures. It's just not going to happen unless we put in more energy. Okay? If it's exothermic and the delta H is negative, and there's less disorder, that is, the sign of delta S is negative, then whether or not the reaction will occur will depend on the temperature present. The reaction is more likely to be spontaneous at lower temperatures, so really cold. If it's endothermic and delta H is positive, and the entropy condition has more disorder, that means the delta S will be positive, which again will depend on the temperature. The reaction is more likely to be spontaneous or thermodynamically favored at really high temperatures. This is something that you just need to know. Later on, I think I show you a diagram that might help with this, but for now, this is just something that you need to know. So, to do an example associated with this, for example number 3, it says at which temperature does the reaction below become thermodynamically favored? Well, the reaction below becomes thermodynamically favored when we calculate what that temperature is. So the formula will be change in energy will be equal to change in enthalpy minus temperature times change in entropy. Okay, and I've given you some information already. Now in this case, because I'm trying to figure out the temperature at which the reaction will become thermodynamically favored, I'm going to do my calculation assuming I'm at equilibrium, so I'm going to give delta G a value of 0. Delta H was given to me as 180.7 kilojoules per mole minus temperature, which is what we're solving for here. And this unit I'm going to change to kilojoules per mole because kilojoules is our currency of chemistry. So 24.7 joules per mole times 1 kilojoule over 1,000 joules will give me 0.0247 kilojoules per mole. So I'm going to plug that in here, 0.0247 kilojoules per mole. So when I solve this out, I get a value for T to be equal to a positive 173.3 kilojoules per mole. What?
For the unit on it?
Oh wait,
Should
per mole Kelvin. Sorry.
Per mole Kelvin?
No, I'm sorry. Hang on. Kelvin. Sorry. I just. Oh wait. Sorry. Stop thinking. This is my fault. I was copying down the wrong problem. Well, I copied the right problem, but then I copied the wrong answer. Don't oh my gosh me. Okay. Anywho, we're good. So this should still be 0, but temperature in this case should be 7,316 Kelvin. That's much better. Now, let's talk about this for a second. Delta H is negative, so that means it's exothermic, has a negative value, right? It's what? Oh, sorry, positive. It's positive. It's positive, right? And then in this case, the delta S is also positive, right? Right?
Yes.
And delta G has to be negative at really high temperatures. So we haven't calculated what delta G is yet. We're going to, but I'm telling you that in order for this reaction to be thermodynamically favored, we have to have an incredibly high temperature, which is, in this case, 7,316 Kelvin. Does that make sense? Now, with example number 4, okay, I'm going to calculate the value for delta G. So, in this case, I'm going to take delta G, which is equal to delta H minus T times delta S, and I'm going to be solving for delta G in this case. I know that delta H is 180.7 kilojoules per mole. The temperature that I was given in this problem is 298 K, and I'm going to multiply it times the delta S, which I have to change to kilojoules, which we already did before, with 0.0247 kilojoules per mole Kelvin. So in this case, I have 0.0247 kilojoules per mole Kelvin. Now, when I go through and I calculate that out, I get a delta G value, in this case, to be a positive 173.3 kilojoules. Now, going back to our chart, okay, if delta G is positive, will this reaction occur at that temperature? If we calculate that delta G is positive, will the reaction occur?
Absolutely not.
No, because it's nowhere near 7,000 K. So in terms of assessing whether or not something is thermodynamically favored or not, we have to keep these 3 quantities in mind. Sir?
What would actually like make the temperature better? Because just
We
looking
look
up
at the
and the
temperature of the
sun,
sun.
it on the surface the sun is only 5,700.
So what does that tell you about this reaction?
It's definitely non-spontaneous.
Correct.
Wait, can you go further? Yeah, can you say it?
Which part?
The fact that it's
What I said or what they said? Okay. So what I'm saying is that based on my calculation of room temperature, 298 K, right? Given the values that I was given, my delta G is positive. Okay? When delta G is positive, that means that the reaction is not thermodynamically favored. And when we compare it to example 3, we determined that in order for the reaction to be thermodynamically favored, we have to be at 7,000 K. Does that make sense?
Delta G be measured in kilojoules. Should just be kilojoules.
In this case, it's just kilojoules per mole. Okay, now, does that make more sense? Example number 5 says zinc can be extracted from the industrial ore sulfurite, ZNS, zinc sulfide. Evaluate whether the process to extract zinc will be thermodynamically favored. So, looking at this reaction, is this reaction thermodynamically favored? A lot of you are shaking your head yes. You are wrong.
Aha!
What is the reaction saying? What is the question asking?
If it would be thermodynamically favored.
When what happens? If we extract zinc from ZNS. The way that this reaction is written is it is thermodynamically favored going from zinc and sulfur to zinc sulfide, but it is not thermodynamically favored going in the reverse reaction. So you want to be able to look at these and understand what the question is asking. So this is not thermodynamically favored. So this is not thermodynamically favored. For the reverse reaction, for forming zinc. Okay. Now, Looking at the next one, evaluate whether the process will be thermodynamically favored if the reaction is coupled with the combustion of sulfur to form sulfur dioxide. Yes, because if I change negative 198 to positive 198, which is what it would be going to zinc, and then I add this reaction, I'm still going to be negative, aren't I? Do you follow that? And if I'm still negative, that means that yes, this is thermodynamically favored.
Okay, can you just repeat that?
Okay, so we're still trying to get zinc. Okay? But if I combine these two reactions in the same system, one of them is clearly thermodynamically favored. The sulfur plus oxygen makes SO2, yes. Okay? But it's so thermodynamically favored that the thermodynamically favoredness of it is more than the reverse reactions change in Gibbs free energy, and as a result of that, we can get zinc.
Okay. That's cool.
Yes?
So you're comparing like the Ford reaction with the sulfur reaction?
Yes.
Okay, not into the system.
I am comparing the reverse reaction above with the forward reaction below.
So imagine when. Wait, why'd you say that's positive one?
Hang on. So what I'm getting at here is that the value for delta G for this reaction going in that direction is negative 198, correct? But this reaction is actually asking about the formation of zinc, so going in this direction, okay? So that means that going in this direction, delta G is really 198.3. Okay? Now if I say that the reverse reaction and the forward reaction of this are going on at the same time in the same system, then I take 198.3 plus negative 300.1, and I get a total negative 101.8 kilojoules per mole, right? And as a result of that, I can get zinc out. We good with that?
Yeah.
All right, moving on. This is a formula that you will absolutely see on the AP exam. It is also on the back of the orange periodic table we use.
Oh, it's appendix B now.
It talks about appendix B. It might be D.
Not
I don't know.
appendix B.
Might be B. I don't know. Anyway, it's an appendix is what I'm saying. You have to remember a couple of things. That delta G formation and delta H formation have some similarities between them. Delta G formation of just elements like I2 or Cl2 or Al is going to have a delta G formation of 0. Delta G formation values can be added together using Hess's law to find the change in energy of the Gibbs free energy of the reaction. Coefficients can multiply the free energy formations, and reversing a reaction flips the sign. And because we can couple them together, the reaction can be a reaction that is highly thermodynamically favored, can drive a reaction that is not thermodynamically favored, so the overall process is, which is what we just talked about in the last slide. Okay. Now, here's an example. In this case, I have the reaction of phosphorus and chlorine and making phosphorus trichloride, so it's tetraphosphorus. And what we're going to do here is we are going to use this formula. Delta G is equal to the sum of the delta G formation of standard state of the products minus the sum of the delta G formation at standard state of the reactants. And in this case, delta G is going to give me, for my products, since I'm looking at this part here, I'm going to take, oops, the sum. So it's going to be 4, because that's the coefficient, times the value that I was given of PCl3, which is negative 269.6 kilojoules per mole, minus the sum of my reactants. So in this case, my reactants have a coefficient of 1 and 6. So in the case of the 1, it's going to be simply 1 times 24.4 kilojoules per mole plus 6 times 0 kilojoules per mole. Okay. And I am showing the 6 times 0 because I'm trying to prove the point that chlorine is its elemental state. It has a standard change in Gibbs free energy of formation of 0, as we just discussed. So the overall change in Gibbs free energy in this particular reaction ends up being a negative 1,002 kilojoules per mole. That's where I'm going to apply the brakes for the day. You have a test tomorrow. So homework will do like Monday or, well, closer to Tuesday probably. So closer to Tuesday. I'll see some of you.